So we're going to finish up today's discussion on index of refraction and geometric optics. And so we talked last time about index of refraction n being equal to the ratio of the speed of light in vacuum to the speed of light, or namely the speed of a wavefront, the speed of a traveling wavefront in a transparent medium, okay, which is going to be somewhat lower due to all the superposition effects going on. And that's also equal to the ratio of the wavelength in vacuum divided by the wavelength in the medium. And we also saw last time Snell's law, which tells us about refraction of light beams, light rays at an interface between two media. We say n1 times the sine of theta 1 is equal to n2 times the sine of theta 2, where these angles are measured from the perpendicular with the interface, or the normal from the interface. So if this is some surface between two materials, medium 1 and medium 2, and you have a light ray that's traveling through here. Get a better marker than that. Then when the ray of light enters into the second material, it's going to refract in some way, and this angle is theta 1 and this angle is theta 2. So just be careful about what angle you're measuring, and this is n1 and n2. Okay? So why don't we start with just a little quick review question here. So which of the following are true for a beam of light passing from a medium with index of refraction n1 to a medium with index of refraction n2? And there are several different statements. If n1 is less than n2, the light will bend toward the normal. If n1 is greater than n2, the light will bend away from the normal. Both A and B, neither A and B, or we can't actually say unless we know the values. Okay, so we have a sizable vote for both A and B. Some people say just A. Okay, not many people answered E. So let's take a look at this. It's certainly true that if we say that N1 or N2 here, what do we say? N1 is less than N2. So this is N1 less than N2. So for example, if this were air has an index of refraction of N1 equal to 1.0029 or thereabouts. And if this were water, N2 being equal to about 1.33, here's a case where N1 is less than N2, and you would in fact see the light ray being bent towards the normal, and that's true all the time, okay? So that's a general rule we can use. So certainly at least A is true. What about B? Well, here's the opposite case, right? If N1 is water, N1 is 1.33, and N2 is 1.0029. Certainly is going to be the case that at least sometimes we're going to see the light bent away from the normal, but what also can happen? What did we talk about last time? Total internal reflection. So you got to be a little bit careful, right? It's not going to be the case that always the light is going to be, or in fact, it's not always going to be the case that you have refraction, right? And if you reach some critical point, you're not going to have refraction anymore. You're going to have total internal reflection. And how do we calculate that critical point? What's the condition? Okay, so in other words, theta 2 is equal to what? 90 degrees, right? That's sort of the maximum amount of refraction you can have away, and anything beyond that, we're talking in total internal reflection. So I would say that most people went for B because it seems logical, but you got to be careful about multiple possibilities, right? I mean, certainly this is possible, but it's not the only possible case. This really is the only possibility here. Except for the case where there's no refraction at all, if you have the light ray entering straight down in perpendicular to the surface. But in this case, you could have refraction away from the normal, or you might have no refraction at all. Okay, so that's going to be true for cases where it goes from a higher to a lower index of refraction. So if we look at that critical case, at least for the case for water, we worked this out. We said theta 2 equal to 90 degrees. So N1 sine theta 1 equals N2 sine 90. Sine 90 is just 1. We could figure out this critical angle for any two indices. And so we worked it out for N2 being 1.33 and N1 being 1.0029. And for water, the angle for air-water interface, the critical angle is 49 degrees. So which of these is true? You have in which case will total internal reflection occur? Beam of light and water at 49 degrees to the normal encounters water-air interface. Beam of light and air at 49 degrees encounters the water-air interface. Both of them, or either one? Okay. Certainly A, right? Beam of light and water at 49 degrees to the normal encounters the water interface. So if you have that, that's the critical angle for this water-air interface. This is 49 degrees. This is 90 degrees. So any larger angle than that is going to cause total internal reflection. But what about the other direction? If you have a light ray, so here's air, and here's water. Here's an angle of 49 degrees. What's going to happen to that beam of light when it goes into the water? It's going to go closer to the normal, okay? So it's a one-way thing, right? You have to be going from a higher index to a lower one. If you're going from a lower one to a higher one, going from air to water, there might be some reflection. We've seen reflection off of a surface of a pool or pond or something like that, but it's not going to be total. So there's going to be some light refracted through, and that light is going to be refracted towards the normal. And so the angle here will be less than 49 degrees. So total internal reflection is kind of a one-way street. All right, it's only going to occur when you have light beams traveling from a higher to a lower index of refraction, not the other way around. Okay. Questions here? Okay. And of course, this has all kinds of fun uses. Let's see if we can actually do it. So here is kill the lights here. And if I plug this in, just got a nice little array of lasers all kind of lined up in parallel lines. And if I grab something like this, just try to put it right here. Can we see that? So what's happening? There's total internal reflection going on at two different points, right? Because it goes through this high index material, some sort of plastic or plexiglass or something, and hits this surface at a 0 degree angle with the normal with this surface. So it goes through undeflected. But then essentially you've got a surface here that is where the interface is tangent to the curve here, right? And so this is at a angle higher than the critical angle between this plexiglass material and air. Okay, so it's trying to go from a higher index to a lower index, but it's bigger than the critical angle, and so it's going to be totally internally reflected. And again here, and then it comes out somewhat diffused, but coming out the other end. And there's no transmission through that point. Okay. And you can do things like this, where so it's going straight through there. That's not terribly exciting. But if I do something like that, and you basically can make what's sometimes called a light pipe. Okay, you have some glass or some high index material, and you have a light beam traveling through it that travels along the pipe, being totally internally reflected at every interface. Okay, so it just happily travels along, and this has important technological uses in what? Fiber optics, right? And so we've got ourselves here a fiber optic Christmas tree, right? Because that's the most important application of fiber optics, right? And if I plug this in, well, it would help if I plugged it in. So I don't know if you can actually see this too well, but we've got a light. Okay, so we have just a string of little fibers here, plastic fibers, and can we see the endpoints there, where the light's coming out at the end, right? And light's just shining through, and it's got a little color wheel on it to make it change colors, so it looks pretty. And you can see if you look at the fibers from the side, they don't look like any light's shining through them. Okay, there's very little, if any, transmission of light coming out of these fibers through the edges. So the only light coming out you see is at the very end points. So it's no matter how I bend these fibers, the light's being totally internally reflected. And so we can get a light signal to propagate along a wire, a tube, basically. And so that's useful for communication purposes, sending data, cable TV, etc., telecommunications through in a way that has very, very low transmissional losses. Okay, it's much better than electric currents in that regard because you don't have a lot of power loss. So that's important technological application. Okay. So, questions on any of this?